Thank you. So I'm going to talk about a couple of things I've done with V. Arvind and Steve Chain. Okay, so the determinant, I mean, this is something that we all know about, but let me just go through it. So the setting that I'm working in is that I have an n by n matrix with elements coming from, so this is the difference from the standard setting. The elements are coming from some sort of non-commutative ring, right? And what I want to do is compute the determinant of this matrix. Well, how's the determinant defined? It's defined in the usual way. This is how we know the determinant of matrices over fields. Note that in a non-commutative setting, this is probably not the only way to define the determinant. I mean, I could have chosen any ordering of each monomial, and for most of the talk, whatever I say will work with many different natural orderings, but I'm going to stick with this one for now. So this is the determinant of an n by n matrix with entries coming from some non-commutative ring, and I want to compute it. Okay, so and in general, I need to be able to work over an underlying field. So I'm going to assume that my ring contains a field inside it. So it's like a non-commutative extension of some field. In general, it's some sort of algebra. Okay, so I want to compute this object, and I'm going to be looking at two facets of this question. One of these is a circuit complexity question. Thinking of this as a formal polynomial, how hard is it for arithmetic circuits to compute this polynomial? Are there arithmetic circuits of polynomial size computing this polynomial? And secondly, the algorithmic question. So in a sense, an arithmetic circuit that computes this polynomial is like a program that works over any algebra, any non-commutative algebra, and in a sense it gives me a very generic program to compute this polynomial over very many domains. So in the algorithmic question, I want to restrict this question and ask how efficiently can we compute this as a function over various specific non-commutative algebras. So an example that is worth keeping in mind is that I want to compute the determinant of an n by n matrix where the entries of the matrix are themselves little matrices. Okay, so there we are working over the algebra of some maybe d by d matrices, and we want to compute the determinant over that algebra. Okay, so now for what d is this actually efficiently computable? That's the kind of question I want to ask in the algorithmic case. Okay, so let me tell you a little bit more about each of these questions. I'll start with the algorithmic question. I'm then going to go to the circuit complexity question, and most of the time I'll be talking about that. Okay, right. So now, as we all know, we can use Gaussian elimination to compute the determinant of an n by n matrix over any field. As it turns out, the fact that we can divide over fields is not really that important. We can in fact compute the determinant of an n by n matrix with entries coming from any commutative algebra, as long as we have, I mean, multiplication and addition are reasonably efficient operations, right? So now. The question that we are looking at here is if there is an efficient algorithm to compute this thing over specific non-commutative algebras. It turns out that this question hasn't really been looked at much, and it's not known even when the algebra is fairly simple, let's say 2 by 2 matrices over the rationals. Okay, so and the reason it hasn't been looked at is there's not much motivation. Why would we want to compute such a thing in the first place? Okay, well, the answer to this is actually fairly nice. It turns out that this provides a kind of approach to approximate a very related but hard to compute function, the 0-1 permanent. Okay, so let me tell you a little bit more about this connection. So for now we are working over, say, the rationals, right? There is no non-commutative algebra, and we know in this very restricted setting that the permanent is very hard to compute, even if all the entries of the matrix are just 0 or 1, right? So we know that the permanent is an extremely hard function. And in this setting, it turns out that for many applications, even an algorithm that gave an approximate solution to the 0-1 permanent would be interesting. So we want an algorithm A such that for any 0-1 matrix X, the value of A of X is within 1% of the permanent. Yeah, and it's not at all clear whether such algorithms exist, and it's a fairly surprising fact that they do. So in a famous result in 2000, Jerome Sinclair and Vigoda proved that you can in fact come up with such randomized algorithms. But it turns out that these algorithms are, for one, it's not clear why such kinds of algorithms, they're based on Markov chain techniques and so on. It's not clear why such an algorithm is necessary to compute the permanent. And secondly, they are not really very quick. I mean, they're polynomial time, but they're still run something like n to the 7 time, even after improvements, and they're fairly complicated. So what I'm going to tell you about another kind of approach to approximate the permanent that originated sometime in the early 80s. And the idea behind this approach is reduce computing the permanent to computing the determinant. Okay, so recall that so we want to compute the permanent of this matrix X. So I haven't really defined the permanent, which is probably a bad idea. Let me just write it down here so that is this portion visible to everybody? Yeah. Okay. So the permanent of a matrix, of an n by n matrix, is very similar to the determinant. It's got the same terms, only without the sign. Okay, so that's the permanent. And what we want to do is, given an n by n matrix with real numbers, in fact only 0, 1 entries, we want to compute the permanent of this matrix. It's suspected that this is a fairly hard problem. Okay, so but let's say we do want to compute it. Note that it's extremely similar to the determinant. So a natural approach that suggests itself is to actually reduce it to computing some sort of determinant. And Gotzel and Gutmann sometime in the 80s came up with this extremely simple and nice idea. They said that, okay, we have this matrix X, let's multiply every entry of X by a random plus or minus 1, random number from plus or minus 1. Okay, so we now have a random matrix Y with the property that every entry of Y is either Xij with probability half or minus Xij with probability half. Okay, so say we look at the determinant of this creature. So something that's extremely surprising and also very simple to prove is that if I look at this particular random variable, the expected value of this random variable is exactly the permanent of the matrix I started out with. Okay, so very nice. So we note that this random variable is extremely efficiently computable. It's just the determinant of a 0, 1 matrix over the reals or something. So use Gaussian elimination. Okay, so we have this random variable Y, which is extremely easy to compute, and the average value of this random variable is exactly the value we want to find. So immediately a very simple algorithm that comes to mind is, well, run this random experiment k times, you get k different random values of Y, output the average. Okay, so you get y1, y2, yk, output the average value of these. Okay, so the question we want to answer, for example, is how good is this algorithm? In other words, I mean, obviously each iteration of this algorithm is efficiently doable, but how many times do we need to run it so that we can be reasonably confident that the output will actually be what we want? Yeah. And this kind of thing, this kind of algorithm has been looked at for many different problems in the literature, and it turns out that the answer here depends really on the variance of this random variable Y. So if the variance is very large, this algorithm needs to repeat this, the iteration needs to go on many times. The variance is very small, then we are in good shape. Okay, so what Gotzel and Gutmann showed is that, sorry.
So how many times?
If the variance is, so essentially the number of the variance number of times, essentially. So k is right. So we will look at the variance of this random variable right now. Yeah, so it's not clear what the variance of this random variable is. So I'm just going to tell you what it is, right? So what Gotzel and Gutmann showed is that in fact the variance of this random variable is something like 1.7 to the n. So we need to run this algorithm that many times to actually be reasonably confident that we are getting a value close to the permanent. Okay, so note that yeah, this is not is not very ideal. We want a polynomial time algorithm. But at the same time, it's not completely trivial in that it's not clear if 1.7 to the n is easy to achieve or something. The trivial algorithm for permanent is of course n factorial, compute each other terms. Even if you use something a little more sophisticated like Reiser's formula or something, you still get a 2 to the n time algorithm. Right? Yeah, you're right. So we are only approximating. You're right. So it's a randomized algorithm for approximating the permanent that runs in time 1.7 to the n, which is nice.
Sorry, the term that depends on the approximation factor is lower order than 1.7 to the n?
Yeah. So this is going to be within 1.1 or something like that. So so I've kind of normalized it so that you're like within 1% of the permanent.
Once you do it, you can add another small exponential factor.
Right, that's true. Yeah, that's right. Okay, so right. So now, okay, this approach is not really giving us polynomial time algorithms, but it seems extremely simple, and hopefully it can be extended to give something better. And it turns out that it can. People have looked at this. sometime in 1993, Karmarkar, Karp, Lovage, Lipton, and Luby actually extended this algorithm where now the random matrix Y is no longer the product of the original matrix Y with the original matrix X with plus minus one random variable. It's now each entry of Y is actually a product of the corresponding entry of X with a random complex number. So the random complex number can be a random cube root of unity or a random fourth root of unity and things like that. And they actually studied this problem. It turns out that the variance of this random variable is actually better, and the expectation of the square of this absolute square of the absolute value of this matrix actually turns out to be still the determinant of the matrix we started out with. Okay. So they said, okay, they analyzed the variance of this, and they actually found out that this algorithm runs in time something like 1.4 to the n. Okay. So
you'll be getting complex guesses, right?
right. So the if I can just go back here, the random variable is really like the absolute value squared. So I'll always get a real number. So
What did Barvinock do?
right. So Barvinock, what he did was he looked at larger matrices and he analyzed the variance, but he could not. I'm sorry. He came up with an efficient algorithm for a slightly different notion of determinant, but he could not really analyze the variance. So his work is kind of okay. It's closely related, but slightly tangential to what we're doing. So, yeah. So right. So it turns out that when we go over the complex numbers, we actually get a more efficient algorithm. Chien, Rasmussen, and Sinclair sometime in 2003 looked at an even further extension where they looked at the quaternions. So if you don't know what the quaternions are, don't bother. It turns out that they are an algebra that contain the complex numbers, and again there is an absolute value and a norm square defined here, and it turns out that if you do substitution in these guys, you actually get an algorithm that runs in time 1.2 to the n. So all this is very suggestive. In some vague sense, as your domain is getting bigger, your variance is getting smaller, and your algorithms are getting more efficient, right? And so the question is, what next? Okay. So what next? It turns out that all of these guys are actually sitting inside the algebra of 2 by 2 complex matrices. Okay. So now this gives you a natural hierarchy to try to extend your algorithms in. So try computing a determinant over complex matrices. Well, of course, now we are in the non-commutative domain, but already here we are in the non-commutative domain. So it turns out that even here, the algorithm actually needs to compute the determinant over a non-commutative domain. And what Chien, Rasmussen, and Sinclair do is not quite compute the determinant, but a small variant that's enough for this purpose. But it's not clear here anymore. No, so that's the thing. So they don't actually compute the determinant. So for the quaternions, they can get away with some sort of trick which falls short of computing the actual value. They compute something called the Dieudonné determinant, which is for the purpose of this algorithm sufficient. Okay. So so now the natural question is if we can compute the determinant over these larger creatures and actually get down the running time. Well, it's not clear if we can compute them. It was not known if we could actually do the computation efficiently, but it was known that we could actually get down the running time. So it turns out that if you can efficiently compute the determinant over larger and larger real matrix algebras, say for now, then we can actually reduce the running time to a small exponential. So for example, when c becomes like 100, this epsilon sub c is going to be like 1 over 100. So it's going to tend to 0 as c tends to infinity. Right. So we get algorithms that run in time 1.01 to the n, 1.001 to the n, and so on. Okay. And they also showed that if you can actually extend this algorithm to compute the determinant over n by n real matrices. So remember that this is an n by n matrix with n by n real matrix entries. If we can actually compute the determinant of this object, then we can in fact efficiently approximate the permanent in polynomial time. So then the variance is down to polynomial. Okay. And so this is one of the reasons for trying to look at how efficiently this determinant object is computable, and so on. Okay. Right. So now, so this is where we came in. So in a result sometime in 2010, we showed that this approach is not really very likely to work. It turns out that if you want to compute the determinant over n by n matrices over some field, you can in fact use that algorithm to compute the permanent exactly over that same field. So since that seems to be a very hard problem, we can't really hope to do this. Right. And so this kind of
F doesn't need to be large.
Sorry?
Compared to n.
No, f does not need to be large. Right. That really works over any f. Yeah. So in particular, this approach is not very good in coming up with efficient estimators that run in polynomial time, but one can still ask if this is still a feasible option, and it turns out that it's not. So let's say we had a finite field. For simplicity, let's work over prime fields. If the determinant over even 2 by 2 matrices over that prime field can be computed in polynomial time, then the permanent over that prime field can be computed in polynomial time. Okay. And it's suspected that this is hard for any prime not equal to 2. Okay.
This is not true over complex numbers?
Sorry?
This is not true over complex numbers?
Oh, actually it is true over the complex numbers as well. Yeah, so I should have written any field of characteristic not equal to 2. So, okay, even that's not right. So, FP you can also take in the rationals, the complex numbers and so on. So,
isn't it easier? So, is this the implication you want to have? I mean, if you can count the determinant in the matrix rings, then...
Right, so this is a weaker theorem than this in a certain sense.
I don't know. Constant times identity matrices from the ring, then...
Right, so if you could compute the determinant over large matrix algebras, then you could definitely do it over small matrix algebras, but the converse is
I mean the first theorem, you
right.
say that if you can count the determinant over the matrix ring, then
right.
you also can do it over the field.
No,
I can compute the permanent over the field.
Oh, okay, okay.
Right?
Sorry.
Yeah.
That,
Okay.
that makes more sense.
Okay.
Give me time to read the second, please.
All right. So yeah. So these are results, and so this is what we have regarding the algorithmic question. So it's possible that some sort of variant of the Gaussian-Gutmann approach can still yield efficient estimators for the permanent, but this naive approach that requires computing the determinant exactly is probably not going to work. Maybe something that involves computing a small variant that still is good enough for these algorithms might work. Okay. All right. So let me now talk about circuit complexity. Yeah.
The results also work if you are allowed to approximate it within a constant? Or do
Yeah.
you have to be exact?
Yeah. So I'm sorry. Are you saying that is this problem hard? I mean, is it hard to approximate the determinant? Do our results apply that? No, we need to actually compute it exactly.
Exactly.
Yeah. So it's not clear. Yeah. Okay. So now let me talk about non-commutative circuit complexity for some time. And so what is the question here? Again, so we are now in the world of arithmetic circuits. What is an arithmetic circuit? So suppose I have some finite field f, some field f and a set of variables x1 through xn. An arithmetic circuit that computes a polynomial over these variables is a very simple creature. It's a very simple thing. It's formally it's some directed acyclic graph. It takes as input. It takes at the leaves are the input variables of the polynomial and some constants from the field. And what it does is it uses simple arithmetic operations, addition and multiplication, to compute some polynomial. Okay. So now the difference from the most standard setting of arithmetic circuits here is that the multiplication at these multiplication gates is actually non-commutative. So here all the action is happening in this ring where x1, x2 is actually a different creature from x2, x1. They are different. And so every multiplication gate should really come with a left child and a right child, and when you multiply them together, the multiplication in this ring takes place in that order. Okay. So obviously now we are interested in computing polynomials as efficiently as possible in this model. Okay. So now a non-commutative circuit computing a polynomial f in this ring fx, you should really think of this, or at least I think of this, as an algorithm to compute this polynomial f over any algebra over the field. Okay. The reason is that this circuit in a sense makes no use of any sort of commutativity relations that might hold over your algebra or whatever. So for example, if I had a circuit that computed a determinant, right, I could use this same circuit to compute a determinant over 2 by 2 matrix algebras over the field, over 3 by 3 matrix algebras over the field, and so on. It makes no use of no relations that actually are present in the algebra. Okay. So it's like a very generic thing. So it's to have a non-commutative circuit is kind of harder than having an algorithm that works over 2 by 2 matrix algebras. That's the point I'm trying to make here. Okay. Yeah. So now, and as usual, we want to measure the efficiency of such an algorithm using the size of the circuit, which is simply a number of vertices in this direct acyclic graph. Okay. So, all right. So now let me also go through a couple of special models where this problem is interesting. So now one of these models that I'll be looking at is the model of formulas, where the circuit is kind of restricted in that the underlying undirected graph is actually a tree. Okay. And one more model that's very useful, but and has been looked at in the literature, is the model of algebraic branching programs. So these things look kind of unnatural the first time you see them, but there's actually a very natural reason for looking at these things. So a non-commutative algebraic branching program formally is simply again a directed acyclic graph. Now we have two important nodes, the source node and the sink node of this graph, which will play an important role. And it's important, so the edges of this graph are actually going to be labeled by linear forms over my variables. Okay. So now I have this kind of weighted graph. The weight of every edge is some sort of linear form over my variables. And now what is the polynomial computed by such a creature? It turns out it's defined as follows. So I look at every path from S to T. There are a bunch of linear forms that appear along the path. I take the product of all these linear forms in order, because here it makes you have to actually specify which order in which you are doing multiplication. And then what I do is I add this up over all possible paths from S to T. Okay, so this is the polynomial computed by this ABP. All right. So and the way I have defined it, an ABP with d layers, in which every path from S to T is of length d, computes homogeneous degree d polynomials in the non-commutative ring Fx. So you can also look at ABPs that compute inhomogeneous degree polynomials by adding a constant term in these linear forms. But for the purposes of this talk, I am going to stick with this model because it's going to be useful for some reasons. And so the size of this thing, again we have to there's some notion of size, which is it's simply a number of vertices in the underlying graph. Okay. Right. So now I've defined three different models of non-commutative computation. I defined circuits, I defined a restriction of these called formulas, and then I defined ABPs. Okay. So now how strong are each of these things? It turns out that any polynomial that has a formula of size s has an ABP of size s square. So formulas are not really all that much more efficient than ABPs. And this is actually a fairly easy fact to see. So if you go back to ABPs, so suppose I had two different algebraic branching programs computing polynomials f1 and f2. Suppose I just composed them in series, in the sense that I identified the sink of the first guy with the source of the second guy. Then it's easy to see that the polynomial I'd now be computing is simply the product of the two polynomials that these guys compute. Okay. And similarly, if I had two ABPs computing polynomials f1 and f2, and I kind of compose them in parallel, in that I identified the source nodes and I identified the sink nodes, then the polynomial I'd now be computing is the sum of the two polynomials that I was computing. Okay. So if you can compute f1 and f2, you can compute f1 times f2 efficiently, compute f1 plus f2 efficiently, and your sizes are kind of adding up. So this straight away tells you that you should be able to compute all formulas efficiently. Yeah. So the only problem with my construction was that at the base level, these formulas could be using constants and things like that, and the ABPs that I would end up with would actually be kind of inhomogeneous. So the way I've defined it, I'm only looking at homogeneous ABPs. So if the formula was indeed computing a homogeneous polynomial, then through a process of some sort of homogenization, one can actually construct an ABP, a homogeneous ABP that computes the same polynomial, but there's a small size blow up. It's now s squared.
Because what you described would have been s, right?
Right, what I described would have been s really, it would have been linear, but you can actually, in the process of homogenization, you lose a factor of s. Right. Okay. And in a fairly similar but and very simple fashion, you can show that any ABP, any polynomial computed by an ABP of size s can be computed by a circuit of size s square. So circuits are at least as strong as ABPs, ABPs are at least as strong as formulas. Okay. And of course, a natural question to ask is, are any of these inclusions actually strict? And it turns out that we do know something here. We know that circuits actually are strictly more powerful than ABPs. This inclusion, on the other hand, we don't know if it's strict or not. Okay. So that's what I'm going to talk about now. So the first person to look at lower bounds for a non-commutative circuit model was Nissan, who showed that any non-commutative ABP computing, for example, the determinant polynomial must be of exponential size. So, in contrast to the commutative model where we look at commutative polynomials and so on, and where we don't have any possible lower bounds at all. Here it turns out that even for fairly natural polynomials, we can say that any ABP, for example, computing them must be of size 2 to the omega n.
So what underlying field does this assume?
So this works over any field, right? And these lower bounds have been extended. So Chien and Sinclair showed that if you have any non-commutative ABP which is computing the determinant over some sort of some specific algebras like 2 by 2 matrices and so on, then it must be of size 2 to the omega n. Now what this statement means is the following. So again they show that any non-commutative, if you have a non-commutative ABP computing a polynomial f which might not be the determinant but which agrees with the determinant over, let us say, the 2 by 2 matrices, then this particular ABP must be of exponential size. So, it is really a considerably stronger lower bound that applies for a large family of polynomials. Yeah? And in contrast, note that this is in contrast to the commutative case. When we look at commutative arithmetic formulas, we really have no super polynomial lower bounds for anything. Okay, right. So, as I said, we do know circuits are more, so we have lower bounds for ABPs, and but it turns out that when we look at the more stronger model of an arithmetic circuit, we have no explicit super polynomial lower bounds. So though it seems like the non-commutative model is actually easier to prove lower bounds for formulas and ABPs, we have all sorts of lower bounds. For the most general arithmetic circuit model, we are still kind of stuck.
For an upper bound for determinant, is there a polynomial size ABP?
In the commutative setting, there is. Yeah, that's right. Okay. Right. So let me look at a closely related question here. So another question that people fairly often look at in the commutative setting is the question of how powerful, how different these two polynomials are with respect to their circuit complexity. One of them is the determinant that we have already looked at, and the permanent, which I defined over there on the board. And it's a really important problem in arithmetic circuit complexity in general is to separate the complexities of these two polynomials in the commutative setting, right? So we suspect that the permanent in the commutative setting has no sub-exponential sized arithmetic circuits, but on the other hand, we know that the commutative determinant has polynomial sized arithmetic circuits. And it's a huge open question to actually see if there is this difference between these two polynomials. And a natural question to ask is does this dichotomy hold without the assumption of commutativity? Is commutativity crucial in making this go through?
The determinant is complete, right? So if there is something that has some non-polynomial bounds in the permanent.
Right. But by something, right. Right. So if there is something in the arithmetic version of NP that has a super polynomial lower bound, then the permanent does.
So that's true in the commutative case.
In the commutative case and in.
It is true in the non-commutative case.
Yeah, it's true in the non-associative case. Yeah.
But then you had to define the permanent carefully. So I'm not sure.
In the non-associative, you have to define it carefully. In the non-commutative,
so
I think it's pretty straightforward.
I think the permanent defined in this exact same way is still complete in the non-commutative case. Yeah. So right. Okay. Yeah. So the question we'd like to ask is, does this kind of difference hold in the non-commutative model? Okay. And the philosophy here is that understanding their relative complexities in the non-commutative setting might help us understand what really makes them different. Yeah. So it's known, in fact, from Nissan's result, as I said, that the determinant requires ABPs of exponential size, and the same result also holds for the permanent. So they are, ABP complexity is not really going to separate these two in the non-commutative setting. So what we have to do is look at circuits. Okay, and the result we prove that I'm going to talk about now is if the determinant does indeed have. So it turns out that in the non-commutative setting, the setting is completely different from the commutative setting, in that if the determinant is actually efficiently computable in the non-commutative setting, then it turns out that so is the permanent, right? So this is like a complete break from the the commutative setting. Actually, it depends on what you do, on how you define the reductions in the notion of completeness. So, the reduction we use, so the most standard notion of reduction allows you to substitute variables by other variables or constants, but our reduction is a little more general, and hence it works only in the non-commutative case. I mean, that kind of reduction would work anywhere. So, yeah, so it's complete under a more generous notion of reduction.
It's still a fairly low complexity reduction.
Right, it's fairly low complexity. What we do is actually substitute matrices instead of substituting field elements.
Size.
No, polynomial size matrices. Okay. Yeah. So what I'm now going to do is I'm going to go through the proof of this thing. Okay. So I'm going to show you how to reduce the permanent from to the determinant in the non-commutative setting. Okay. So the proof. So before we go through the proof, we need to look at this notion of an ABP a little more carefully. So recall this thing. This an ABP is a directed acyclic graph which computes a polynomial in this way, and so let's just recall something very simple, a simple combinatorial fact about graphs.
So basically, you will have now to compute some permanent of some matrix, and then you will describe some bigger matrix whose entries will be matrices, and
Exactly.
the determinant of it will be the permanent.
Right. Absolutely. Yeah. So right, that's right. So the determinant of that matrix with matrix entries will actually be a matrix, but one of the entries of that will be the permanent of the original matrix. Okay. So yeah. So before we go into the reduction, it's probably going to be helpful to look a little more carefully at this ABP model. Recall that the ABP is this directed acyclic graph. Paths in this graph define products of linear forms, and the polynomial computed by this thing is just the sum over all paths of the polynomial computed by each path. Okay. So and it's going to be recall that if I have a directed acyclic graph G, this is a simple combinatorial fact that probably most of you know. Let's say this directed acyclic graph G has an adjacency matrix A. If I look at powers of this graph and I look at the ijth entry in that power, it's really the number of walks really from I to j of length t. Okay. Walks, paths, they're the same thing. Okay, right? And this is going to be useful in the following sense. So let me look at what I call the adjacency matrix of an algebraic branching program. So what's an adjacency matrix of an ABP? Here I think of this as a weighted directed acyclic graph. Between any pair of vertices I and j, if there is no edge, I just put in 0. If there is an edge, I put in the linear form that labels that edge. So that's the adjacency matrix of this ABP. Okay. So now if I start looking at the powers of this thing, if I look at a to the d, recall that this ABP has d plus 1 layers, so every path is of length d. So if I look at a to the d and I look at the stth entry, s is the source, t is the sink, then this is exactly the polynomial computed by a. So in computing a to the stth entry of a to the d, I'm going to look at exactly, I'm going to look at every path from s to t and I'm going to sum up.
So I sort of missed this before, but are you assuming that?
I'm assuming that
there's some notational thing that it's not the same polynomial that's being applied at every layer. I mean, they're the same concept.
the same what?
So I'm not sure how you think of this, but each layer has a different form that's being applied.
It's not just each layer, each edge has a, each edge is a different form. So
The only important thing is that all the paths are of length exactly d. So
Exactly.
that's why we wanted homogeneous.
exactly.
G is the entire graph.
Yeah, G is the entire graph.
Okay.
Okay. So yeah. So when I look at powers of this adjacency matrix and I look at a certain entry in the power, then I get the polynomial computed by, okay, this should be the ABP, not A. Yeah. Okay. Right. Yeah, some, not just some entry, the stth entry corresponding to the source and the sink. Yeah. Okay. Yeah. So now what is going to be, so note that, so what is A? So every entry of A corresponds to an edge in the, possibly an edge or a non-edge in the ABP, and if there is an edge, I actually have a linear form. So I can actually just split this matrix, and it's going to be helpful to write it like this, right? I can write it as, I can split every entry as some linear form in x1 through xn. So, I can in general write this matrix as a1 times x1 plus a2 times x2 plus an times xn, where these guys only have field elements a1, a2 through a. Okay. And the reason this is going to be helpful is that now if I want to think of the coefficient of a certain monomial in my polynomial, it's going to be very easy. What I do is, if I want to compute the coefficient, for example, of xi1, xi2 through xid, then all I need to do is compute the product of the corresponding matrices and look at the stth entry. Okay, a very simple observation, but it's going to be kind of useful. Okay, so now let's see how immediately how it is useful. So it turns out that this can be used in a fairly simple way to perform our reduction from the determinant from the permanent to the determinant. So let's assume for now that P is some ABP which computes some polynomial G in our n variables that come from a matrix. So remember that our determinant was actually a polynomial in these variables, and now this ABP is computing some polynomial G over the same variables. Okay, let's say that the adjacency matrix of P is this creature. We have just factored out. So these are all matrices that contain only field elements. Okay. So now we are actually going to come up with the reduction from permanent to determinant. We are going to start. So assume that the determinant over this field is actually computed by some small circuit. Then what we can, as I said earlier, you should really think of the circuit as being able to efficiently compute this polynomial over any algebra containing the field. So it's a very general object, right? So in particular, I can probably substitute. This gives me an efficient algorithm to compute the determinant over n by n matrix algebras and things of this nature. Yeah. So in particular, we can compute this thing. So what I'm simply going to do is I'm going to substitute for x11 the matrix a11 times x11, for x12 the matrix a12 times x12, and so on. Okay. So now what is the point of doing this? Well, note that the output of this thing is actually going to be a matrix of polynomials. Okay. And this thing is going to be efficiently computable, because in a sense the determinant was efficiently computable over any non-commutative domain, and you can actually come up with a circuit for this matrix of polynomials by actually hard coding by replacing x11 by n squared variables which correspond to the entries of this matrix, and x12 by n squared entries, and so on. Okay. So when we expand this polynomial, this matrix of polynomials, what we really get is this creature. Okay. So f of x, so I've just expanded I'm just using a definition of the determinant. This is sine sigma times this thing, right? And if you really write it out, so now if I look at, for example, the stth entry, the stth polynomial in f of x contains like it's a matrix of polynomials. So I'm looking at the stth polynomial. The stth polynomial, its coefficient is going to be the polynomial is going to be sine sigma times the stth entry of this matrix times this monomial, and the stth entry of this matrix is simply the coefficient of this monomial in the polynomial G. Okay. So okay, what have we accomplished? We have not really much, but what we have managed to do is we've been able to see that if we start off with an ABP computing some polynomial over the same set of variables, we can use this ABP to kind of modify the determinant in a kind of fundamental way and come up with another polynomial that's efficiently computable but possibly slightly different. Okay.
You want to present something itself?
Right. So what I would like to do is find what would be really nice is if this was actually sine sigma. Then sine sigma times sine sigma would actually become 1, and this would actually become the permanent, right? But I'm not really going to be able to do that, because as I said earlier, the determinant really cannot be computed by an efficiently by an ABP. So I'm going to have to do something slightly different. Yeah, but that's a general idea. Start with the determinant and use this process to actually slightly modify the determinant and get the permanent. Okay. So yeah. Okay. So this trick that I just talked about leads to this fairly natural definition. So I'm going to define the notion of product between two polynomials. Let's say I have two polynomials in the non-commutative ring fx. I define their Hadamard product to be the product in the following sense. So what I do is that I look at these two polynomials as vectors, right? For every monomial there's a coefficient, and I just take the pointwise product of these two vectors, and that's a polynomial. That's the new polynomial I get. Yeah. So for example, and a kind of instructive example is that if I take the determinant and I take its pointwise product with itself, its Hadamard product with itself, then I get the permanent.
Wait, why do you get permanent?
That's because every coefficient of the determinant is either plus or minus 1. When I take the Hadamard product, I'm going to square the coefficient. So I'm just going to get 1, and hence I get the permanent.
Coefficient plus 1.
Right. So I'm just taking the pointwise product. Okay. All right. So yeah, and what we essentially showed is that in a sense, the set of efficiently computable non-commutative polynomials is kind of closed under this Hadamard product. So, for example, so what we showed is actually in this for with f being the determinant, but the same proof works. We showed that if f is computed by a circuit of size a small size and g.
The determinant times the determinant is a permanent because you look only at 0, 1 entries or.
No, for I take any monomial, right?
But is it the product? So it should be the same coefficient, like not the square of the same coefficient, right?
So yeah, just the coefficient. So I just take, right, I just multiply their coefficients. So if I take the determinant, for example, each one of its coefficients is either 0, plus 1 or minus 1.
The coefficients in the
Right? Yeah. So corresponding to monomials in the permanent, they're all going to end up 1. Of course, the others are never going to come in. So that's it. Okay. So all right. So the importance of this notion is that is this. So we've seen that essentially if f is efficiently computable by a small circuit and g is efficiently computable by a small ABP, then the Hadamard product of f and g is actually computable by a small circuit. Okay, so in some vague sense, we can if g is efficiently computable, we can get another polynomial that's efficiently computable by hitting f with g.
So, but for applying this, you know that the determinant isn't efficiently computable.
It's true. So we'll probably have to.
You're not going to be able to use
Yeah.
this for g. Okay.
Right. So yeah, we are not going to use this with f and g both being the determinant. We are going to do something else.
Sorry, was this not the thing you just proved?
Yes.
G over
Exactly.
Can you show that just for a second?
Yeah.
Okay.
So I mean the proof of this is actually fairly simple. So I'm just doing this with f being the determinant, for example. So let me start with the determinant. Yeah. It's what I'm just doing is I'm plugging in the matrices that come from this ABP. It's a11, x11, so on until an, xn. And when I just expand the definition of the determinant, what I really get is the same thing. Only in addition there is this term here, which comes from the ABP, right? And therefore, if I look at the stth coefficient, which really corresponds to computation in the ABP, I get the coefficient of that same monomial in the ABP. So I just get the same coefficient that the determinant gave me times the coefficient in the ABP, which is what I was looking for. Okay. Yeah. So this is where I am. Yeah. So the idea is again going to be I start with the determinant, and that's going to be f, and I'm going to hit it with some polynomial, and I want it to end up being the permanent. Okay. And as has already been pointed out, we can't use the determinant in place of g. So we're going to have to be a little cleverer, but not much more. Okay. So assume that the determinant is efficiently computable. Again, the idea here is to use a very efficiently computable, in other words, computable a polynomial g that's computable by an ABP to turn f into the permanent using this notion of Hadamard product. And the polynomial g we come up with will be extremely simple. All of its coefficients will be either 0 or 1. So you can think of this g as simply a filter polynomial. So you got the determinant which has got lots of coefficients. G simply filters some of them out, and somehow that already looks like the permanent. Okay. So a fairly simple process. Okay. So well, if we are going to do this kind of filtering thing, it better be the case that the polynomial g, the monomials it actually filters out, are all of the same sign, because it's got to look like the permanent. In particular, all the entries of the permanent have the same sign. The sign has disappeared. Yeah. So what we are going to do is actually work with a slightly bigger determinant. Yeah. We are going to start with f being the determinant of a 2n by 2n matrix. This will have 2n factorial monomials. The polynomial g is going to filter out n factorial monomials from f, all of the same sign. Okay. Yeah. So and then it will almost very naturally start looking like the permanent. Okay. Right. So this is exactly what we want to do, and obviously what we want to do is we want the resulting thing to look like the permanent. So there should be some sort of natural correspondence to the monomials of the permanent. Okay. So how do we come up with this natural correspondence? Well, there's a very simple candidate over here, and here's the trick. So for each pi in Sn, for each permutation on n letters, we call that we have a 2n by 2n determinant, and we want to compute, say, an n by n permanent. So for each term of the n by n permanent we want to compute, consider the term corresponding to this permutation in the determinant. Okay. So what does this permutation look like? It says, okay, take 2n letters, apply pi in a sense to the first n letters, and apply pi to the second n letters separately. There is absolutely no correlation between the two. Okay. So, well, it's easy to see that since pi is applied twice, every transposition kind of appears once here and once here, and therefore the sign of every such permutation must be 1. Yeah. So this is very simple. Yeah. Okay. So what we'd like to do is use g, use the polynomial g which has exactly those terms of the determinant that kind of occur here, that kind of look like this. Okay. So I want a polynomial g which is efficiently computable by a small ABP, and the only terms of the determinant that it has are these terms. Note that among the terms that are not, that don't appear in the determinant at all, the ABP could have all sorts of garbage. We don't really care, right? Because what we are going to do is take this Hadamard product thing, and for terms that don't occur in the determinant at all, the corresponding coefficient is 0, so it's never going to bother us. So what's kind of helped us here with this notion of Hadamard product is that we don't really need to care about those coefficients. Among coefficients that appear in the determinant, we want the ABP to compute a polynomial that satisfies the property that it contains exactly these monomials.
The coefficients that monomials that don't appear in the determinant are the ones that have higher powers on the axis?
Or that don't correspond to permutations at all. For example, x11, x12, I mean, things of that nature.
Higher powers if it was commutative, right?
Right.
Yeah, okay.
Yeah. So yeah. Okay. Right. So we want to filter out exactly these guys. And now the question is, can this be done? Okay. So it turns out that even such a polynomial is not really computable by a small ABP, right? And the intuition for this is that you should really think of this ABP as, and it looks like it's like an automaton, like a finite automaton really. So a finite automaton that sees its variables and decides, if it's going to.
Log space program?
It's like a log space program, right? It's like a log space program that needs to kind of accept only these monomials, right? But if it's going to accept only these monomials, the only way to do it is to compare this thing with this thing, this thing with this thing, and so on until this thing with this thing. So in particular, at the middle point here, it's got to remember this entire permutation.
So now I'm confused. What is the input to this automaton?
Right. So the input to the automaton. So this is just vague intuition. So the input to the automaton is in a sense the monomial string. So the ABP computes a polynomial, right? And this polynomial is going to have coefficients 0 or 1. So in a certain sense, what you should think of this ABP as doing is like defining a function. It decides to accept some monomials and it decides to reject the others, right? The monomials that correspond to coefficient 1 are the ones it decides to accept. The monomials that correspond to coefficient 0 are the ones it decides to reject, right? And if you think of it as computing a function this way, the function is actually very efficiently computable. It's just like a.
So each path is sort of filtering out a number.
No, actually that's not what I'm saying. I'm saying that you should think of this. No, each path need not filter out a monomial. So I'm saying that this ABP, whatever it computes, it's computing a polynomial that has only 0, 1 coefficients. Just think of this as a function for now, right? Think of this as computing a function that accepts some monomials and rejects others. It may compute this function in a fairly crazy way, in that it may not be that every path filters out a monomial or any such thing. But this function is efficiently computable in the following sense. So you can think of an automaton that, okay, let me just actually just go through it. Yeah, so here's the ABP, right? So I can think of this as an automaton in the following way. I start at this particular state, right? And now let's say I get as input a long monomial, a monomial of degree d. I'm going to decide whether to accept or reject it. So what I'm going to do is kind of go to this state and store the coefficient that I have here. So let's say I get as input a monomial xi1, xi2, so on until xid. So what I do is that, okay, so it's kind of vague in the sense that I decide to go to one of these states with a certain weight. So xi1 appears on this linear form, and so on until this linear form, each with a certain coefficient. So I kind of branch into all these states with a certain weight. And similarly from here, let's say the next input to my ABP is xi2. Then from here, I branch to all these states with different weights corresponding to different weights that xi2 has in all these edges. And in the end, I'm going to get to t in all sorts of different ways corresponding to all sorts of different paths. And the sum of the weights that I've accumulated along all these paths is actually going to tell me whether to accept or reject the ABP. I mean the monomial, right? So this is it's a fairly complicated way of defining modular computation, but if you really think about this process of computation can be done very simply, like, say in log space as you said. Right, it's a product of matrices, exactly, yes, and this was what was kind of visible here as well, right? I mean, yeah. So yeah, it's just a product of matrices, so it can definitely be done in log space, right? So right, so it turns out that as a result, if there is to be a small polynomial sized ABP to filter out exactly these monomials, well, it seems like that such an ABP would have to store this entire permutation and kind of have to check these guys, and therefore it seems like this kind of thing is not possible, because in particular the number of states that would in a sense be required here seems to be exponential. Okay, you can, right? That's exactly right. So what we are going to do is exactly take that and interleave it, right? So now what we do is that we look at the same permutation, only now we are going to look at pi 1 followed by n plus pi 1, pi 2 followed by n plus pi 2, and so on. And now, so these are the monomials. This is the monomial that's going to correspond to the monomial that corresponds to pi in a sense. Yeah. So now it looks like this kind of thing can be efficiently done by an ABP, because all it needs to do is remember this, check this off against this, remember this, check this off against this, and so on. Okay. So this permutation rho of pi I have defined is again, it's again the same permutation that we had, the 2 copies of pi, only they are interleaved. So it turns out that since there are 2 interleaved copies of pi, the interleaving doesn't really make that much of a difference to sign. It turns out the sign of rho of pi, it's no longer 1, but it's now independent of pi. It's just some plus or minus 1, some constant. Yeah, depending on n. Yeah. So
So an ABP for this might accept terms more than a permutation, but it
Absolutely.
be absent in the determinant.
Absolutely. So you don't really care what it does to non-permutation monomials. It will accept lots of those, but you don't care because the determinant is killing them anyway. Okay. So what we are going to do is filter out for every pi in Sn the monomial in the determinant that actually corresponds to this permutation, which of course looks like this. Yeah. Okay. So now the only thing to do is to see that this thing is efficiently computable. It turns out, so the question is, can we filter out these good monomials? And the answer is yes. In fact, it's an extremely simple polynomial. So all it needs to do, as I said, is check that the first what it sees in the first place, the I it sees here is n whatever, this thing minus n, the j it sees here is this thing minus n, and so on. So it does this comparison, and this is the formula that computes this particular filtering polynomial. Okay, so it's just x1i times x2n plus I, sum over all I, then similarly for the next 2 guys, and so on. Okay, so extremely simple. And so what I've given you is really an efficient formula computing this thing. And as I told you earlier, formulas, anything that can be efficiently computed by a formula can be efficiently computed by an ABP. So there is of course going to be an ABP for this object. Okay, right. So we've taken this filtering thing and we actually filter out exactly the monomials that I talked about, these things. Now already, of course, now all these guys have the same sign, so the sign is no longer an issue, but it's not quite the permanent of an n by n matrix. The problem is these guys are all of degree 2n. So is that really an issue? It turns out not to be the case. I mean, this is almost the permanent. We just have too many terms. So all we do is drop all the even terms by substituting by 1, and what we have is the permanent. Okay. Yeah. All right. So that's essentially it.
So how simple would it now be to describe how does this matrix looks, the things that you are computing the determinant of?
Right. So
There's matrices.
so it's a 2n by 2n matrix.
2n by 2n, and in every place you have an n by n.
Right.
Matrix.
Roughly an n by n matrix.
To see what this matrix is, you have to look what these ABPs are. And
Right. You have to look at the coefficient.
or
That's a good question. I'm not very sure. So yeah, it's probably not very nasty. It's only going to have all the matrices are only going to have 0, 1 coefficients, but I don't know if there's any further structure to them. Yeah.
It's not a black box.
Right.
and it will be the coefficient of something.
Yeah, it will be the coefficient of something. So that's it.
Like you're given the
lemma, though.
What's the coefficient of the ABP?
Oh.
Where the matrices for each
So,
part of
s-
the ABP?
so the, you stated the lemma, but about, is it immediately obvious? Is it obvious that you can do this Hadamard that you
before stating the lemma. So, let me just go back there. So, this process is exactly the proof of this lemma. So, what I did was I started off with this polynomial g that is computed by an ABP, and I substituted these matrices that are derived from the ABP inside this polynomial, and what actually pops out is the Hadamard product, right. So, only I have done it in a kind of restricted setting where I only look at one of the polynomials being the determinant, but the same thing works for any polynomial, right. So, the Hadamard, this is the proof of it. Okay. So, yeah, so that's it. So, essentially that completes the proof. So, nothing we have done is really blown up the size by too much. Taking the Hadamard product definitely does not. We have done some substitutions here that definitely does not blow up the size. So, if we had a small circuit computing the determinant, we would end up with a small circuit computing the permanent. And note that this is in fact a non-commutative circuit. So, I mean, so in a non-commutative setting, the permanent is actually, the non-commutative permanent is actually easier than the non-commutative determinant, or at least as not harder. Okay, so it's kind of weird. Okay, so I'm almost out of time. So let me just mention that whatever I said almost immediately yields an algorithmic hardness result. So suppose I wanted to compute the determinant of an n by n matrix with n by n matrix entries. This immediately says that that's hard, because what did I do? I started off with a polynomial, a function computing the determinant. I plugged in certain matrices inside it and became the permanent, right. So if I'd actually used the determinant to compute the determinant of those matrices, then I would have kind of ended up with a permanent I would have actually ended up computing the permanent of the matrix that I wanted to compute. Okay. So essentially what we have shown is that if I had an efficient algorithm to, in fact what we have shown is if you have an efficient algorithm to compute a polynomial f over any non-commutative domain, so this is what we showed for circuits really. So if we had an efficient algorithm computing f over any non-commutative domain containing f, which is an arithmetic circuit for f, and then we had a small ABP for g, then we have an efficient algorithm to compute their Hadamard product over any non-commutative domain. Okay. What we use for algorithmic hardness is a little more restrictive. If we have an efficient algorithm to compute f over say s by s matrices over f, and we have something like a size s ABP for g, then this is exactly the size of the matrices we plugged in here. So then we get an efficient algorithm to compute their Hadamard product, but over the base field. Right. So in particular, we've shown that computing a determinant over something like n square cross n square matrices is at least as hard as computing a permanent. So now this n square can be brought down to any n to the epsilon by a simple padding trick, like a padding trick. I mean, you can blow up the size of the matrix so that n square really is like n to the epsilon. So it's not really very okay. It's very easy, right? Yeah. So as I said, so this already shows that computing a determinant over large matrix algebras is a very challenging task, and one can ask if this thing continues to hold over constant sized matrix algebras, say over the rationals, for example. And turns out the previous approach won't work, because we needed to plug in matrices corresponding to the size of these ABPs, and these ABPs need to be at least like polynomial size to compute that filter polynomial, so to speak. Yeah. It turns out that you can kind of formulate a slight variant of the approach where the size of the ABP is not important, but only its width, but even that we have not really been able to make work. So but what we can do using that approach, which is fairly trivial, is that we can turn permanents of constant size matrices into determinants of constant size matrices. So we showed how to turn large permanents into large permanents into large determinants by substituting large matrices. But if you only want to turn small permanents into small determinants, we only need to substitute small matrices. It's a fairly trivial observation. Yeah. So, but it turns out that even this can be fairly useful, and using this we can actually show that the determinant over even constant size matrices is hard to compute. And the reason for this at a very high level is that we go back to Variance proof that actually looks at and shows that the permanent is hard to compute. So we know that the permanent is hard to compute because a very hard counting problem, sharp SAT, reduces to computing the permanent. And if you stare at the proof relies on various, it's a very combinatorial proof, technical, and it relies on various gadgets. I mean, these gadgets are like 4 by 4 matrices, their permanents satisfy all sorts of identities and so on. and you can show that such gadgets don't exist for the commutative determinant, because if they did, then the determinant would be very hard, right. And but what you can do is you can turn the Hadamard, and you can show that there are such gadgets with the permanence satisfying all these identities. But that's great, because we can turn these gadgets into small determinants of small constant size matrices using a Hadamard product trick. So we can just stare at these gadgets and turn them into small determinants, and then what we will be left with is a large determinant of small matrices.